Okay, so what I'm going to cover in this lecture, so we are going to do some review of what we have discussed. Right, so let's start with the homework problems, and then I will be answering your question if you have any. So problem 1 in homework 1. So you have given basically 3 vectors, v1 in an orthonormal basis. So think about it like a Cartesian coordinate. V3, 0, 5, 2. So first A, we want to see whether these are independent set or not, right? So how did you do this to check whether they are independent? So some constant, right? So some constant like C1, V1 plus C2, V2 plus C3, V3, if it is equal to 0 and all those C's are equal basically to 0, if it's trivial solution, then these are independent, right? So if I basically form this, then put them in a matrix, all of these basically V vectors. So I'm forming this matrix 1, 2, 0, 3, minus 1, 4, 0, 5, 2. So let's call this matrix E. So if I have this matrix, if I can show that the determinant of this E is not 0, right? So what is going to happen if it is 0? Are dependent. If it is not 0, it's going to be linearly independent. So if we calculate the determinant, it's going to be 10. So 10 is not 0, so they are linearly independent. Now in the part B, I'm asking, find this constant. Basically, let's say I have vector W as 5, some constant alpha 6, so 3 components. Find alpha such that it is basically linearly dependent on V1 and V2. So now we want to have this vector basically in the same plane of V1 and V2, right? So what you do in this case? So what is the requirement of the linear dependency, right? So the linear dependency we have, let me use a different color.
If we take the determinant, it should be equal to 0.
So if I have a constant, let's say, I'm not going to use alpha, let's say C1, V1 plus C2, oops, if I can figure out how I can erase with this thing, V2 is going to give me W, right? That's the meaning of the linear dependence. Vector W is linearly dependent on V1 and V2, and C1 and C2 is just a number. So if you write this in an equation or equations, given that we have 3 components, so it's going to be C1 plus, what is the V vector? 3C2, right? Equals to 5. Then 2C1 minus C2 equals to that constant alpha, and basically 0C1 plus 4C2 is going to be equal to 6, right? So now you can compute. Basically, you can compute C2 here. So C2 in this case is going to be 3 divided by 2. Then you can, from first one, you can calculate C1. So C1 is basically is going to be how much? It's going to half, right? Half. And your alpha minus half, or minus 0.5. So that's the meaning of the linear dependence. So problem 2. So we have a vector A as 4e1 minus 2e2 plus e3. And these e's are basically these bases that we have. They are, in terms of the Cartesian coordinate systems, are like this. 1, 0, 1, e2 is 0, 1, 0, and e3 is 1, 1, 0. And the first question I have, basically write it in terms of the standard basis. Standard basis here, nobody asked me this question, but all of you solved it. So it's a Cartesian coordinate, right? So idea is I'm going to plug basically some E1, that's representation from the ijk. So this is ijk, right? So another way to write this, E1 is I plus K here. So that's what really it is, right? So you can basically plug in those 3 basis vectors in terms of ijk inside A, right? And rewrite it. So that's pretty straightforward. Right? So what is going to be A? It's going to be 5. I think it's minus 1, 4, right? Very simple. The reason it is simple is already I have given you the form of the vector in that weird coordinates, right? So you're just going back to the Cartesian. So, and it is easy to go there because you know the expression for each of the basis vectors. Then what I ask here, so is E1, E2, E3 valid basis? Is it? Why? They are linearly independent in R3. That's it. So I'm not going to show that here. Problem 3, so again you have 3 bases. E1, 1, 0, 0. E2 is 1, 1, 0. E3 is 0, 1, 1, right? So those are the 3. So part A, we are going to compute reciprocal basis. Okay, how did we do it? E2 what? Let's say I'm interested in this one. So if I'm interested in EE, I need to write it properly, this one, right? So we use this type of a covariant representation of the basis vector to say that it's reciprocal, right? So what is the formula for that?
Because E3 by determinant of
E2 cross E3 divided by, right? So that's the, and make sure you use this method, right? So you first, because I'm going to ask you to do the reciprocal, then form the transformation rule here, okay? So you first determine these three basis vectors, reciprocal basis vectors. So what did you get? Tell me in terms of I, J, K, or 1, 2, 3, something like that. So what is that?
I minus J plus K.
Okay, I minus J plus K. Good. So this is basically equivalent of this.
Should we write the answer in the form of IJK or minus 1 and 1?
What?
In exam, how should we write the answer?
Doesn't matter. Whichever you're more comfortable. I can grade both. Then you have E2. E2 is going to be E3 times E1. E2 dotted by E3 cross E1, right? So if you do this, this is going to be J minus K, right? 0, 1, minus 1. Then you have E3 So this guy is going to be K. 0, 0, 1. Good. Easy, right? This was the first part, very mechanical. Now in part B, I'm asking this question. What is the representation of the, what was it? Yeah, let's say I have a vector B in part B. If I have a vector A, which is 3E1 minus E2 plus 2E3. So what is the representation of this A in the reciprocal basis? So think about, you have transformed the coordinates and you have gone from the real coordinates to the reciprocal coordinates. So that's the type of transformation we have done. So what would be the,
E is equal to AI, which is also equal to A bar, AI bar, EI bar.
so tell me what, in English, tell me. Nothing on EI,
So we can calculate we can take the reciprocal vectors like coefficients as v1, v2, v3 suppose.
Yes.
And then we can multiply them with the reciprocal of e1, reciprocal of e2 and reciprocal of e3.
Not reciprocal of E1, reciprocal of no. You, when you are doing transformation, what was the transformation rule? I should have it somewhere here. So transformation rule, let's say I'm going from the A to A prime, right? So regular coordinate to primed coordinate system. And this prime coordinate system is a special one here. It is the reciprocal coordinate system too. So we'll mix them together. But it will be interesting. So rule for here, the transformation I am doing this way is that A prime K is going to be E prime K dotted by EI, right? AI. And given that AI superscript I is the real presentation of a vector in my original coordinate system that I have. Right? Okay. The first unit, basically basis vector that you have over there, it's E prime of K. Remember? So what is that? That is not the reciprocal of your original frame. That is the reciprocal of your transformed coordinates. It is the reciprocal of the primed coordinate. But think about it for a couple of minutes. Reciprocal of the reciprocal of the yes, reciprocal of the transformed coordinate. So if you have reciprocal basis of your transformed coordinates, right? Basically, if you that coordinate system, those three E's that we have determined here, these are just going to be the regular unit vectors of the transformed coordinates. Right? Does it make sense? Think about this. Then I need to calculate the reciprocal of these coordinates, 3 I have. So I don't need to calculate. It is going to be the original. Yeah. So that's the rationale here. Everybody got it? No? You are not convinced. Okay. The rule for transformation. Forget the first part of the. Think about it. We have a primed coordinate system that we are going from original coordinate there. The rule is I need to calculate the reciprocal of the primed one. Fine. I have 3 basis sets in the new coordinate system. I'm going to calculate the reciprocal of those 3 vectors. Good? Okay. Now your prime set is a special one. It is the reciprocal of the original coordinate system that we had. So, yeah. Reciprocal of reciprocal, yeah. So in this particular case, when we are doing this type of representation of a vector, that's called covariant representation of a vector. Basically, you calculate the components of the vector in the reciprocal basis, not the real basis. So for that, given that this is a basically primed coordinates is reciprocal of real coordinates. So this is basically this A prime of K that we are writing here. This is actually this component. Okay? And what else we can say? What are the E prime K now? Reciprocal of those things. So what are those reciprocal of those things? E1, E2, E3, right? Okay, so it is interesting. So this basically becomes like AK equal to E, let's write it as EK dot EI dot EI and times AI for this particular transformation. So I'm writing it intentionally like this because I want to get somewhere with this. So what is EKEI in terms of the things that we have defined? No. G. Delta is a little bit simplified, right? It's G. So AK is GKI, AI. So can you tell me what is GKI? So these were your bases, right? GKIs are components that are coming from the dot product of your basis vector. So if I write it here, so let me write it, open it up here. Let's say GKI, I'm going to put everything in a big matrix. So this is going to be E1, 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 E2, E1, E3. So all of them are your E2, E1, E2, 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 E3. And you will have E3, E1, E3, E2, E3, E3. Okay, so you can easily do that dot product. An idea of the dot product that you can do, because we have the components of this E1, E2, E3 in the Cartesian coordinate system. So quickly you can do the dot product. So if you do the dot product, it's going to be 1, 1, 0, 1, 2, 1, 0, 1, 2. So now using this matrix, we can do the transformation straightforward. So if you are coming from the other coordinate system, the prime one, to the real one, in that case, it's the same rule. It's the same thing. So in that case, if I want to get the contravariant components of the vector, let's call it AJs. And this one, GJK, it's the same thing, but now you are doing the disguise. So this is 2, 1, 2, 2, 2, 3. Oops. And you can calculate this too, right? So in this problem, where are these? So we have this, right? So 3. So this is going to be 3 minus 2, 1, minus 2, 2, minus 1. Okay. Any questions? So whenever somebody asks you what is the representation in the reciprocal basis set, basically means that we are looking for so-called covariant components. So as long as you have, you can get it much faster because you don't need to do the first step because that's a redundant step. Okay, so what else do you want to do here? So what is the expression of the A in the what?
2e1 plus 3, 2 plus 3.
2A. Yeah, I have a little bit different. I don't have the final values for A, so I'll add this later, but you can follow that matrix rule over there and multiply it by A, K values, and determine basically this is the transformation rule that you are going to use. All right, do we need to solve problem 4? So it's pretty straightforward, right? So you have two vectors, A as 2 E1 minus E2 plus 3 E3. B is minus E1 plus 4 E3, and I'm just asking what is A cross B, right? So easy way to use this determinant way of doing the multiplication. So 2 minus 1, 3 minus 1, 0, 4. Then you expand the determinant, right? Okay. So this is just going to be I times determinant of 0, 4 minus J 2, 3 minus 1, 4 plus K 2 minus 1 minus 1, 0, right? So you are going to have it as minus 4I It's 8 minus 3 plus 3, 5 minus 5J. Is it minus 5? Minus 11?
Minus 11.
Let's see. Oh, yeah. Yeah. Okay. 8. Yeah. Minus 11. Right. Then you are going to have plus minus 1K, right? So this is your A cross B. Good. Okay, next problem, 5. So you have two, basically a new basis vector. So this one is into 2D, so it has very interesting. So you learned how to do it in 3D and more, but in 2D, might be some challenges. So we have two new bases. So we are calling it e prime 1 and e prime 2. And we have a vector v, which is basically these bases should be in the orthonormal. 4e1 plus 2e2. So we want to find the components of basically v prime in the prime basis. So how did you do this? What? So you followed the transformation rule? Okay, so how did you determine? Because now you have only two, it's a 2D. So how did you do it? Because all of you solved this in the homework.
We went by AI is equal to E prime I multiplied by E prime.
A prime inverse into V.
So what did you write?
A prime inverse into V. V is equal to A prime into V prime.
V equals to what?
A prime into V prime. A prime dot V prime.
What is A prime here?
V prime. A will make a matrix A.
Uh-huh.
2, 1, minus 1, 3.
Okay, so okay, all right. So let's call it. You do what? You make a matrix.
2, 1, minus 1, 3.
2. So this is basically your e prime 1. This is e prime 2. Okay, so then you do what?
Inverse of
Multiplied by the inverse of the V prime into this matrix.
So basically you say v prime is going to be
A prime
a minus 1 times v.
A prime
A prime inverse? What is A prime?
No, this inverse.
What is A prime here?
inverse is which is basically determinant into inverse of this. Inverse of this upon determinant. That will give me inverse.
That is inverse, okay. Yeah. I can get the inverse, yeah, that's fine. But you're saying A prime, what is A prime?
Only of this one, like this matrix.
Inverse.
A inverse alpha by V. Okay, so but why is this?
Because it was in your note, it was written that V is equal to A prime dot V prime.
So okay, so your V vector. All right. So all right. So if I have my V vector as 4e1 plus 2e2, and my V vector is going to be some constant, right? Let's say alpha e1 prime, right? Plus beta e2 prime, right? And this, you can do it in the 3D also the same way, right? Do we know what are the e1 prime and e2 prime in terms of the, we have it, right? So you can replace it over there. I just want to show you how you get that out of blue matrix form, right? So your V is going to be alpha times E1, which is 2E1 plus E2, right? Plus beta minus E1 plus 3E2. Right? Do I know what is V? I know what is V. right? So I have v here. V is not changing, right? The vector it stays the same. Only the representation is changing. So I'm going to replace it over there. So I will have 4e1 plus 2e2 equals to this 2 alpha e1 plus alpha e2 minus beta e1 and plus 3 beta e2. Okay, so now e1s should match with each other, e2 should match with each other. So basically we are solving two equations, right? Do you see the two equations? Right, those two equations here. So one for e1, so I will write 1 for e1. So it's going to be 4 equal, so 2 alpha minus beta, right? Is there anything else?
2 is equal to alpha plus 3 beta.
I can write it for e2, 2 equals to alpha plus 3 beta, right? So if I write it in the matrix form, then it's going to be 2 minus 1, 1, 3 times alpha and beta is going to give me, I will write it somewhere a little bit here because I need to have this space. 4 and 2, okay? So this is basically meaning of this is this. So can I calculate alpha and beta? Right? So the way that you suggested, it is exactly the same thing. It is exactly the same thing. What he called that matrix over there, 2 by 2 matrix as A. So let's look at it carefully, right? So this matrix is what you call as an A matrix. The columns of this matrix is your basis set. Basically, new basis set that you have. 2, 1, minus 1, 3. So this is E1 prime, and this is E2 prime. Alpha and beta here are the components of the vector in the primed notation. I use alpha and beta. You can use v prime 1, v prime 2. Doesn't matter. So I need to multiply it by that. Then you talk about inverse, right? If it's solve it using inverse, I can find the inverse of A matrix, multiply both sides. So basically, my in one shot alpha beta is going to be this A minus 1 times this 4 and 2. That's it. You don't need to memorize it. This works for three-dimensional case too. 4-dimensional, doesn't matter. You can do this trick, always. So by the way, what did you get for alpha and beta? I don't have the final answer. 2 and 0. Okay. So alpha is 2, beta is 0. Basically, your new vector v prime, or not, it's the same vector, sorry. V is going to be 2 E1 prime. That's the representation of the same v vector in the new coordinate system. Any questions about this? Maybe a little bit confusing. So what we did, we know v vector is not changing. I'm calling it alpha, some constant, time e prime 1, coefficient for e prime, and another coefficient beta for the second vector that I have. And then I'm going to just expand it. Instead of writing e prime and e prime 1 and 2, I have the expression of these basis vectors in the original coordinates. So I will just replace it and do just a little bit algebra so I can deduct two equations here and solve. So if I had three bases, so I had three equations. It's exactly the same. And again, backward transformation also works the same. So. Okay, so what else we want to do here? Find a new matrix tensor. Okay, so that is good. So what is, oops, what is G prime ij? So it's a 2 by 2, right? So this is E prime 1 dot E prime 1, E prime 1 dot E prime, oh, sorry, 2, E prime 2, right? So if I do the, where do I have it over there? So it's going to be 5, 1, 1, 10, something like this. Okay. Now we have done some transformation, right? So transformation should be invariant. Basically, the dot product should be invariant with respect to transformation. So this is part B, and in part C, we want to check that, right? So I want to check the original V dot V is what? Original V dot V. What? 20. 4 by 4 plus 2 by 2, right? So 4 times 4 plus 2 times 2 is going to be 20. So this is the, let's call it original. Then I do the same with the transformed, right? So what is that? What? What?
It's just 2E1, right?
2E1?
The transform one.
Yeah, okay. So
You can substitute E1 and find the.
So all right, so let's write this, right? So what is the basic rule for transform? Basically, when we have a vector and we know the prime notation is not orthogonal anymore, so it's going to be what? If you follow the Einstein notation, it's going to be Vi, Vj, your Gij, right? Okay, so we are in the prime notation, so we have this primed, right? Okay, so if you open this up, what will be this? How many components you are going to have? No, 4. There's 4 components, right? So V1, V prime 1, V prime 1. So it's going to be V prime 1, V prime 1, G1, 1. Then what else we have? Where is the matrix? It's here. Okay. Then you have V prime 1, V prime 2, G1, 2 plus V prime 2, V prime 1, G2, 1 plus V prime 2, V prime 2, G2, 2. Okay, so what is going to be? What is your V prime? This alpha was your V prime. V1 prime, beta was V2 prime. Right? So this is going to be 2 times 2 times 5. V prime 2 is 0, that's 0 plus another 0, right? Plus another 0. So this is going to be what? 20. This is great, right?
Can we just find v prime that is 2 times e1 prime?
Okay.
And e1 prime is 2e1 plus e2. So we get the original.
Well, but you are then in that case you are cheating. You are transforming your vector to the original set, right? Because what makes it special to be in prime notation is that your basis in terms of e prime, right? We want to do the calculation in the prime notation, right? So if you do that, absolutely you can do that, but that's the part A. Right. So, but here I wanted you to see the components of the matrix tensor. So these all should be primed, right? If we are in the primed notation, we are doing this calculation. In the first part, we have also the same thing, but the thing is that this G matrix reduces to the Kronecker delta. It's the diagonal element always is going to be 1. Your G11 and G22 is 1, and the off diagonals are 0, and that's why you have that relationship. Okay, in problem 6, what I'm asking is doing some calculate or identity proof. So A dot B, very straightforward, right? So how did you do this one? Defining the vectors, right? So A is AI, EI, B is BJ, EJ, and let's call C as CK, EK, right? So if I do this, it's going to be AI, so the left-hand side is going to be AI, EI, dotted by BJ, EJ plus CK, EK. K should be here. So this is going to be AI, BJ, EI. Oops, this. Oh, sorry, this CK, I made a mistake. Sometimes it's very confusing. It should be down there. EJ. So there's a dot product plus AI, CK, EI, EK, right? And this is just the A dot B, and this is just A dot C. You don't need to do any delta or GIJ or anything. Just very simple. Then in part B, you have A dot B cross C equals to B C cross A and C A B, right? So I will use the same notation for A, B, C. So let's open from this side, left-hand side. So I have AI EI dot. So because it has cross products, so what I'm going to do, I'm going to consider them in an orthonormal basis, easier. BJ CK epsilon JK L, let's say, EL, right? EL. Okay. So this is going to be AI BJ CK epsilon. Okay, then you want to keep L? Okay. But you told me AI.
There won't be another epsilon, right?
No. There won't be another epsilon. There's one cross product, one epsilon. Sure. But you have a choice here, right? But dot product happens between what vectors? Dot product happens between these two. So I'm going to have a delta IL, right? Okay. So if I have something like this, it's either I need to have I or L. I cannot have both, right? So because you said AI, so it's going to be epsilon JKI. Delta goes away. I applied the delta. So that's the first part. Let's say second one. So it is BJ EJ dotted by CA. I will write it as a CK AI epsilon KIL EL so this one is going to be BJ CK AI epsilon KIJ. Okay, so we can consider these two things, right? So that one is the same. So are they equivalent? Do you see why? Well, you can do the two flips to get that, right? So not necessarily clockwise. There is no clockwise IJK. I can change them to JI or JKI. Right, so these two things are equivalent, and those indices that we assign them, it's just very arbitrary, right? So you can change the index and do the name change for each of them. So they are equivalent. So they are the same thing. Okay, this was I believe, all of the homework. Any question about this? So the key problem in this homework, in my opinion, is that you should know basically problem 3 pretty well. Problem 3, because we have two concepts over there. One is how you determine the reciprocal basis. Then, how express the components of a vector in its own reciprocal basis. So I can basically give you a vector, and I will ask you what is the covariant component of this vector. So the reciprocal basis, basically components are the covariant. And the next one is basically the problem 5 is also interesting because you really don't need to do the reciprocal basis to do the vector transformation. just by basically brute force writing the equations, you can get them. It works pretty well for 2 by 2, but as you can see, as you increase the number of the components of your vector, so if you go 3D space, 4D, 5D, it becomes more difficult. So it is not, sometimes that solving that inverse problem is going to be challenging. So we will discuss it in the next chapter when I'm talking about it. Right? Okay, so let's we have around 15 minutes. So let's see how much we can do for homework 2. We have a couple of tensors, A and B. So A is represented by a matrix like 2, 1, 1, 3. So it is a two-dimensional word. B represented by a matrix again, 4, 0, 0, 5. Both of them are symmetric. So we want to do this. A double dot B. So if your A is represented as AI, J, EI, EJ, B is KL, EK, EL, right? So if you do follow the Einstein summation, what is going to be here? Okay. So basically you have a couple of dot products, right? So EI is going to be multiplied by EK, and EL is going to be multiplied by EK, EJ, EL, EI, right? So this is going to be, I will write it the full form of it, BKL. So I will have delta IL, delta JK, right? And those deltas, you can simplify them. So it means that I is equal to L, so I'm going to keep the IJ. So instead of L, I'm going to write J. Instead of K, I'm going to write, let's see, what did I do? So instead of K, I'm writing J. Instead of L, I'm writing I, right? Did I make a mistake? No, I'm okay, right? It's fine. Okay, so if I do this operation, I'm going to have a scalar, right? The key point is there is no vector in it anymore. So it's double dot. So it's going to reduce the order of operation by 4. Each dot product reduces the order of operation by 2. So my left hand, basically, this shouldn't be C tensor. So there is a mistake here. So this should be C. I think I had the same mistake in somewhere in class notes also. It's copy paste mistake. C is a scalar. It cannot be a tensor. Okay, so all right, so if we do this, so the number I have is 23. So you just need to do basically all of those. Basically, this means when we write it as Aij, Bji, if you forget the Einstein summation, it's something like this, right? This is equivalent to a couple of sigmas on I equal to 1 in this case, because this is two-dimensional from to j equal from 1 to 2 aij bji. So you need to write all the basically four components of that summation. You just need to calculate that. Okay, the next problem is pretty straightforward. So you have a tensor T represented by a 2 by 2 matrix, 3, 3, 1, 1. It's a symmetric matrix. We want to find the principal values, basically eigenvalues of this, right? So for getting the eigenvalues, the characteristic equation that we always interested is determinant of this, in this case, T minus lambda I equal to 0. So you need to form that grand matrix here and calculate the determinant of that. So it's for a 2 by 2, it's pretty straightforward, right? So even 3 by 3 is not a big deal. So here I'm going to have 3 minus lambda 1, 3 minus lambda 1. Basically, the determinant of this must be 0. So 3 minus lambda square minus 1 is equal to 0. So it's going to be lambda square minus 6 lambda plus 8 equal to 0, right? So lambda is equal to 4 or 2. You can quickly solve it here too, right? So it doesn't matter. 3 minus lambda is plus minus 1. So you have a couple of eigen values. They are distinct, real. Because we are going to consider those things that they are not distinct. Sometimes you have those weird eigen values that they are repetitive. Basically, so-called they have degeneracy, degenerate matrices, and how we can get the eigenvector or kind of a pseudo eigenvector to describe them, right? So as long as they are distinct, it is easy. And the eigenvectors calculation, I haven't asked here, but it is not a big deal, right? So the way that you do, how do you do that? If you want to calculate the eigenvector, A minus, let's say this is lambda 1 and 2, right? So lambda 1 multiplied by a vector is a vector 0, right? So this is the equation for the first one, and the same thing for the second one. So A minus lambda 2I V2 is going to be again 0 vector. So these are the two equations that will give you the eigenvectors corresponding to these eigenvalues. It works perfectly well as long as these are distinct.
Suppose we get V1 and V2 and the components are not 1, 1. Suppose they are 1, 1, 0. So we have to divide it by the magnitude.
Not necessarily. If you want to use that eigenvector, this principal direction, because it is a direction, really, right? It is better to normalize it, to have it in a nice compact form, because the eigenvectors itself, if you have 3, let's say, if I have these 2 distinct eigenvectors here, they can build a coordinate system for me. Okay? If I want to use that coordinate system, it is better to have a basis vector that they are orthonormal, right? They are going to automatically orthogonal to each other. That's the principle we have here for distinct ones, as long as your matrix also is symmetric. But it is better to also scale them to have the magnitude 1. If you don't scale them, nothing bad will happen. But you need to keep track of the length. That's it. Whatever you're dividing. And many derivations, people scale these vectors in their derivations, so they remove that dependency on your spatial directions that you have, right? So it's better to do that. Okay, so this was okay. So in problem 3, I am giving you a tensor. So we have a stress tensor. So I'm calling this a stress tensor. Sigma represented by a 3x3 matrix, 8, 2, 0, 2, 5, 1, 0, 1, 3. And we want to rotate it 90 degrees around the z-axis. Basically, you rotate the whole plane xy. So let's say I'm looking at this is x, this is y, and this is my z, basically coordinate coming out. So this is my original frame, okay? My transformed frame is going to be what? I'm going to rotate it 90 degrees. So it's like this, I'm going to make it like this. So let's do, basically, this is going to be my x prime, y prime. Z stays the same. So this is the transformation. So you can think about I have rotated. So to avoid to basically draw the same axis, I am using that dashed a little bit of space from the original one, right? All right. So what should we do? So many of you use the rotation matrix. The whole purpose is you derive that rotation matrix, right? This reciprocal basis that I have defined, that gives you a transformation matrix. So in this particular case, it's going to be a rotation matrix, right? So if I told you, okay, I'm not only rotating, I'm also multiplying the scale in the y, basically y prime by 2, by a factor, you cannot use that rotation matrix anymore. Right? So, okay, so how we are going to do this? So tell me what was the rule. So let's say I have the new representation of the tensor this time. I'm calling it T prime KL, right? And I have my original one, I'm calling it Tij. How I'm going to do this? There are two basically sets of this dot products, right? So one of them was E prime K, right? EI. So this was easy. So this was similar to the vectors. But tensor has two things, EI and another one EJ. And I need to do a dot product from the right-hand side this time. So it's going to be EJ dot E, let's call that L, doesn't matter. They are the same thing as the E prime of K. Because I'm getting the KL component. So this is your transformation rule. What are the E prime K and E prime L? These are the reciprocal basis of the transformed coordinates. Reciprocal basis of the prime notation. That's it. So now we are going to do the easy part. Okay, so let me see. I wrote it somewhere. Okay. Let's first identify the prime notation regular bases. That's the first order of business. So let's say I'm asking this question: what is my E prime 1? Based on this transformation here that I have. I am working in a Cartesian coordinate system. XY plane is rotating 90 degrees around the z-axis, counterclockwise. What?
Cos theta.
We can,
Look at this.
the first row is even.
E1 prime is related to the x, right? So let me be more accurate here. This is my 1, this is my 2, this is my new 1, this is my 2 prime basically. So what is the unit, not unit vector, the basis vector if I do this type of transformation? So the unit vector along the x prime is going to be I, no, it is not going to be I.
J.
J. Right? We have IJK. We are expressing everything in terms of the old coordinate system, which is the Cartesian coordinate system. We know it. So E prime 1 is going to be J, or this is your, if you like, write it like this, doesn't matter. E prime 2 is what? Minus I. Good. See, now you know what I mean. So what is the, in terms of the, this is going to be minus 1, 0, 0, right? And what is the E prime 3? Same as this, K. 0, 0, 1. Okay? Good. So this is, sometimes you need to do some geometry. If I ask you to cos, basically theta angle, so you need to do some cosine theta, sine theta to determine that relationship between the transform basis and the original basis. Okay? But this is very good. Why? Because I can quickly write the reciprocal. This is IJK, right? You remember? IJK, they are self-reciprocal. So the reciprocal is the same. So this means that E prime is J. Reciprocal of the E2 prime is minus I. And reciprocal of the third one is again K. This is very good. And you can double check it. Reciprocal basis dotted to the original basis should be delta. So if I do dots between E prime 1 in the reciprocal and E2 prime in the original, so it's going to be 0. So you see that, right? Basically, the dot product of these things is 1, and other pairs are 0. Other pairs from the first row and second. If I pick. All right. So let's call this this is going to be a matrix, right? So this is a matrix. This is a matrix. So I'm going to call it E. Let's call this as a E prime. I'm just naming them, so you can name it whatever you want, right? So this matrix E is going to be E prime. Basically, this is a basis. One E1. E1 prime, E2 prime, E3, then you have for the second one, same thing. should be E1. So they're going to be E matrix. And now I need to figure out this guy on the right hand side, E prime. So that one is very similar to this. So let's call it E prime. Is going to be, so this time I need to do E1 dotted by E prime 1, E1 dotted by E prime 2, E1 dotted by E prime 3, then E2 dotted by E prime 1, E2 dotted by E prime 2, E2 dotted by E prime 3, E three, so you need to do a bunch of dot products. You have the expression for the prime reciprocal basis, was prime 1, right? And you can easily calculate this dot product. But do you see a relationship between these two matrices here?
Transpose.
They are transpose. So we'll talk about what is the transpose. But basically the columns of E is the rows of E prime. So whenever you are dealing with a basic tensor transformation, so you are going to have basically dealing with this type of matrices. Basically, you determine one of them, the other one is going to be the transpose of this. Right? So unfortunately, I don't have the final answer for it. So I will do the calculations. I will add it over there. So basically, you need to do 2 matrix multiplication here to get that basically representation of the. So let's write it like, if I want to show it as sigma prime is going to be E sigma E transpose. So that's in the form of the matrix multiplication. Okay, I'll solve the last one. I will add it to Brighter Space later. So on Thursday we will start discussing about the matrices. So take a look at those notes I have uploaded for second module. And next week, remember, you are going to have a quiz on this first module. Is it? Did I tell you Thursday or Tuesday? Did I? When is the due date for that last homework? Tuesday, yes. Let's do Tuesday. Thursday is a little bit late. We are almost in the matrices. So let's save that for Tuesday.